Greetings everyone, welcome back into Calculus 2. Time to take a little small hiatus and talk about everything in this first unit that we've covered up to this point. This is usually about the point in Calculus 2 when there's a test. So what I want to do real quick in this video, I say real quick, I mean, not necessarily super fast, but what I want to do is go over some problems that are on a test that I've given in the past. This is a test that I have given in a class and represents all of the material from this unit generically as a whole. Okay. Now, one thing I do want to mention, and I say this all the time with tests, right? It's a good thing to keep being reminded of. Don't focus on any one problem. Please, when you study these math topics and any math topics, you should look into the skill set that goes along with the entire method. Do not focus on one individual problem and say, oh, is that type going to be on it? Is this type going to be on it? That's a bad way to study for math. You should look at the method in general and try to get a generic structure to help you parse your way through each individual type of skill. Okay, so don't focus on any one of these problems. These are just good examples of the type of things that are in this unit, because this is a test that would be on this unit had you would have taken this class face to face maybe. Okay, so the topics that are on this first unit are all of the advanced integration techniques: integration by parts, integration using trigonometric substitution, an integration that requires you to split up fractions with the partial fractions method. Along with the trigonometric substitution, there are a lot of advanced trigonometric integrals, so some of those come in as well. Also, we approximated integrals using both the Trapezoid rule and Simpson's rule, so there's some of those. And then, of course, being able to deal with improper integrals that either have infinity in the boundaries of a definite integral or have a discontinuity somewhere in the boundaries of the given integral. Okay, so these are all of the topics that are typically covered in that first test of the Calculus 2 that we have gone through and created here. Here are the first two problems on this test that kind of started off our unit the same way. We have a by parts integral and an advanced trigonometric integral. Okay, so starting here, I know that this is a by parts integral because I've got the multiplication of the two functions and I can't just do an antiderivative of that with a normal substitution or something straightforward. Okay, and I can see with the multiplication that x to the fourth with enough derivatives would go away, and then the e to the negative 5x is what I call a repeater, right? That's the thing where you get the same derivatives and integrals over and over again, right? So obviously this one is a perfect setup for doing a by parts integration, but using the tabular method. So I'm going to set up my table, right, with a u and a v side, and I'm going to place the individual function pieces in each of those spots, e to the negative 5x. And now I'm just going to do my subsequent derivatives of the u until I zero it out. So I'll have 4x to the third, 12x squared, 24x, 24, and 0. And then I just need to do enough antiderivatives on the v side in order to match up all of the rows here, right? So the antiderivative of any exponential is, of course, itself. And then, since this is just a linear exponent here, I'm going to just divide by the constant part of it. It's like a basic substitution. So I have negative 1/5 e to the negative 5x. Then I repeat the process again, and every time I divide by the next power. So I have 1 over 25. Then I have negative 1 over 125. Then I'm going to have positive 1 over 625. And then I'm going to have negative 1 over 3,125. Every time I'm just dividing by a negative 5, right? So it's going to alternate out. Okay. And remember, tabular method, what I'm going to do is I'm just going to multiply diagonals. Can you imagine doing this one with all the biparts? This would be a lot of different bipart stages, one after the other. This would not have been very fun doing the long biparts way. So I'm going to be multiplying in diagonals here. And don't forget, integration by parts, uv minus the integral of e to u. The minus makes these signs alternate. So it starts positive, goes to negative, then positive, negative, and positive. Right? Okay, so then from here, I'm going to start with x to the 4th times the negative 1/5 e to the negative 5x. So I have negative 1/5 x to the 4th e to the minus 5x. Then next I'll have minus 4 over 25 e to the negative 5x. Whoops, I forgot my x to the 3rd. Next, plus a negative, so minus 12x squared over 125 e to the negative 5x, minus 24x over 625 e to the minus 5x. And lastly, I have plus with a negative, so minus 24 over 3125. No x's there, but then the e to the negative 5x. And don't forget your plus c. And then, of course, you can make this a good bit prettier by factoring out a lot of the common pieces. So it looks to me like all of them have a negative. All of them have the e to the negative 5x. And I can actually get a 1/5 out of each one. So let's do that. Negative 1/5 e to the negative 5x times, I have x to the 4th plus 4/5 x cubed plus 12/25 x squared plus 24 over 125x, and lastly plus 24 over 625, and then everything plus c, right? Everything dropped a power of 5 all the way down because I factored out a 1/5 from each one. And then, of course, they were all negative. I changed them all to positive by factoring that out. Much cleaner way of writing the antiderivative there. Okay, next. Next, I have the integral of secant cubed times tangent cubed. Secant cubed of x times tangent cubed of x. When I approach something like this, remember with these advanced trigonometric integrals, what I'm looking for is something that I can do a quick basic substitution on, right? I want to do a basic substitution so that I can make the trigonometry not be a major part of it anymore. Okay, so I'm looking at this and I'm noticing that if I were to separate a secant and a tangent, one of each, that would be a secant x times tangent x, which is the derivative of secant x. What's left over has secant squared and tangent squared, and then I can convert tangent squared into terms of secant. Okay, so let's do that one step at a time here. I'm going to rewrite this as secant squared x times tangent squared x times secant x tangent x dx. Okay, so I separated that out. And remember, what I'm noticing is that this is the derivative of secant x. From here, I can also say that tangent squared of x is equal to secant squared x minus 1. And then it's times secant x tangent x dx. And then from here, I just need to notice that I can actually do my basic substitution now. I simply let my u equal to secant x. And then my du would be secant x tangent x dx. So then you can see right here I'll have u squared, right? U squared. Here I'll have u squared minus 1. And then right here I've already got du. So then the integral becomes a lot simpler to perform, right? Where our integral becomes integral u squared times u squared minus 1 du, in which case I'll distribute the u squared and I can simply do my power rules. So then I have u to the 5th over 5 minus u cubed over 3 plus c. And of course, we already know that u is still equal to secant of x. So then my final answer is 1/5 secant to the 5th of x minus 1/3 secant to the 3rd of x plus c. The next problem is quite blatantly a trigonometric substitution. You can see it right away when you look at the fact that you have this binomial under a radical and nothing on the outside that's worth using in a substitution, a normal, ordinary substitution, right? Something that's of this kind of format is just made a lot easier by substituting in some trigonometry. So that's what we're going to go from here. I'm going to start by using the binomial that's in the radical here. Since I have something squared plus something else squared, right? That's the other part of the trig subs that just screams it, right? It's not just any binomial, it's a binomial of squares. Okay, so in this case, to set up my trig substitution, I like to use the triangle method. It just helps keep the information of the substitution organized. So I'll put an angle theta here. And for the way theta is set up, because of the addition here, I need to make the two legs the things that are being squared. So for 9x squared here, that'll be 3x. And for 16, that'll be 4. Then I'll use Pythagorean theorem. 3x squared is 9x squared plus 4 squared plus 16, right? And then square root both sides, and that gives me the hypotenuse, right? So here, let me write it out. Let's say I let the hypotenuse be c. Then c squared is equal to 3x squared plus 4 squared, which means that c squared is 9x squared plus 16. And that should happen, right? I want to see that kind of binomial again. And therefore, c is going to be the square root of this. So instead of c here, I'll put square root of 9x squared plus 16 is the length of the hypotenuse there. Okay, so from there, from the triangle setup here, I can find out what all of my different substitutions are going to be. First and foremost, I notice 3x divided by 4 is opposite over adjacent. That's tangent of theta. So therefore, 3x over 4 is equal to tangent of theta. I'm going to multiply the 4. So 3x is equal to 4 tangent theta. That's pretty good. Let me go ahead and just follow it through the rest of the way. I'm going to go ahead and divide by the 3 as well. So x is equal to 4/3 tangent theta. That's my actual substitution here between x and theta. And I got the 3 over there because I really need to do dx. So if I take the derivative of x, dx, I'm going to get 4/3 secant squared of theta, d theta. All right. And then, let's see, I need something else. I need to be able to replace the radical as well. Notice if I do the hypotenuse divided by the adjacent, right, that would be secant. So square root 9x squared plus 16 divided by 4 is equal to the secant of theta. Not a coincidence that I'm coming up with the same thing here. That's an old adage for doing things this way. Whatever new trig function you come up with here, you should go ahead and look at the definition of that new trig function. Okay, one multiplication left here. I have square root 9x squared plus 16 is equal to 4 times the secant of theta. That's one of the pieces I can use in my substitution. I can replace this radical. And then I already have something for x, I can replace x. And I have something for dx. I can replace him as well. Okay, so let's go with that. I'm going to use those 3 pieces to substitute here. So then this is equal to the integral. Dx is 4/3 secant squared theta d theta divided by x squared is 4/3 squared tangent squared theta. And then the square root itself is just 4 times secant theta. So times 4 secant theta. Okay, so let's do some reduction here. I can take out this 4/3 with one of these, and one of these secants wipes out with him. And since this is a division by the leftover 4/3, I'm going to pull out a 3/4 times a 1/4, right? Because this 4 here is going to end up being a 1/4 as well. Okay, and then let's see, what am I left with here? I have integral of secant theta divided by tangent squared theta d theta, like so. Okay, not always an obvious connection, although secant and tangent do go very well together. I can still simplify it a little bit more and make it, a little bit nicer. Okay, so here we go. I'm going to have 3/16 integral. Secant is 1 over cosine theta here. And then I'm going to do times. Now be careful. I'm dividing tangent. And remember, tangent is sine over cosine. But since I'm dividing a fraction, I'm going to flip it. So tangent is sine over cosine. If I flip it, it'll be cosine over sine. And notice it's squared. So both of these should be squared d theta. Okay, so I can reduce a little bit more. This cosine will wipe out with one of these, leaving me with 3/16 times the integral of cosine theta over sine squared theta d theta. Now this is a substitution I can do. Cosine theta d theta is the derivative of the sine theta. Okay, so I can do another substitution. I can go one more level of substitution deep here. I'm going to let u equal to sine theta. So then du would be cosine theta d theta as promised, right? Okay. So then what I have is 3/16 times the integral of 1 over u du. 1 over u squared, I'm sorry. 1 over u squared. Okay, then. The 1 over u squared actually probably would be better to write it as just u to the negative 2. And then it's a power rule, right? I end up with 3/16 times 1 over u, right? The new power is negative 1. Divide by the new power just makes this thing negative. Let's see. Okay, so now let's start opening up the layers of the substitution again. Okay, so I've got negative 3/16, and then 1 over u is 1 over sine. 1 over sine theta. 1 over sine theta is just cosecant theta, though. Okay, so I have negative 3/16 cosecant of theta plus c. Okay, then I come back one more layer. Cosecant of an angle is the hypotenuse divided by the opposite. So this cosecant of theta right here, I can see, is just the division of this hypotenuse by this opposite of the angle. So this is negative 3 over 16 times the square root of 9x squared plus 16 all over 3x plus c. And then notice, of course, the 3's can reduce, and I can multiply everything through. So final answer, I've got negative square root 9x squared plus 16 all over 16x plus c. Now we need to talk about improper integrals. This problem and the next one are going to be improper integrals. Here's the first type, or one of the two types, I should say. This one has a discontinuity. There's no obvious improper pieces to it, but remember, you're supposed to be paying attention always to a function's domain, especially when you're doing a derivative or an integral on a certain portion of that domain. In this case, I'm attempting to integrate from 0 to 4 over a function who is undefined at x equals 2. And it's not just a break, and it's not just a hole. This particular discontinuity is an infinite vertical asymptote type. Negative 1 over x minus 2 is a graph, has a graph, right? If you go to 2, put a vertical asymptote, it would look like this. So if I'm going from 0 to 4, right, if this is 2 right here, here's 3, here's 4, that means I'm trying to look for the area, basically, right, if you want to think of it in terms of area. The area starting at 0 here and encompassing the region that has this asymptote in it up to right here at 4, right? If I do 4 here. So that should be a dead giveaway for you that this particular integral is most likely not going to be defined properly, okay? It's definitely improper, but it's also not going to be defined as far as an answer. One argument you might try to throw at is, oh, well, the infinity here and the infinity here are symmetric and they cancel each other out. You can't do that sort of thing, okay? You cannot just add and subtract infinities willy-nilly like that. Okay, so in this case, what I need to do is to properly split this up, okay, into two separate integrals. And that's where the killer is, okay? The killer of this thing is I'm actually going to have to integrate these two pieces separately because it's a discontinuity. I can't just add up everything across it. So instead, this is what I have to do. I have to break this into the integral from 0 to 2 dx plus the integral from 2 to 4. And even redefining it this way still is improper, but at least now it's a noticeable improper. You can see the 2, and that's an undefined point. So technically, 2 itself cannot be the boundary because I can't actually obtain 2 from the domain of the function I'm integrating. Instead, I have to use limit terminology. Okay, so here I'll have the limit as a approaches 2. Now notice where I'm at. This is from the left only. Approaches 2 from the left. And then it would be the integral from 0 to a, negative 1 over x minus 2 dx, plus completely separate integral, therefore completely separate limit. The limit as g. The limit as g goes to 2 from the right. Integral from g to 4. Now again, notice this limit is from the right because I am coming from the other direction in order to approach 2. And it's still of negative 1 over x minus 2 dx. So this is the only proper way to handle that integral. I can't just integrate across a discontinuity, and I can't even actually use the discontinuity number because it's not actually defined function value for me. Next, I can actually do the integrals now. Of course, it's the same antiderivative in both. The derivative of the x minus 2 is just 1. So really, this is a du over u situation. I'm just going to have an ln here. Okay, so equals limit as a approaches 2 from the left. And I'm going to have the negative ln of the absolute value of x minus 2. And then this is going to be evaluated from 0 to a. Plus, I still have the limit as g approaches 2 from the right. I'm going to have the negative ln, absolute value x minus 2, like so. It's the same antiderivative. And then this is going to have to be evaluated from g to 4. Okie dokie. So then the a portion is the only portion where the limit really does anything. So I have the limit as a approaches 2 from the left. And I've got a negative ln of a minus 2. Absolute value a minus 2, like so. Now, okay, this is approaching 2 from the left. So right here, a minus 2, a is going to be something less than 2. Okay, and be careful. So the absolute value here is actually necessary. It's actually absolutely necessary. Minus negative, so it's plus. And then if I were to plug in 0, I'd have the ln of negative 2. But absolute value, so it's just the ln of 2. Okay? Plus, now here's the thing. Go ahead and just look at this limit for a second. If a approaches 2 from the left, that means a is getting closer and closer to 2 here, which means this whole thing is approaching the ln of 0. right? Which, remember, goes to negative infinity. Okay? However, it's a negative of that, so it's going to approach positive infinity, which you should expect. Look, it's exactly what's happening on the left-hand side. So just this piece by itself is infinity. Although it's really not good form to use that. The only reason I'm getting away with it here is because it is the answer to a limit. However, it is not the answer to the integral. I cannot say an integral equals infinity. Okay, infinity is not a specific value that I can just assign. There's so many different types of infinities that it's not even funny. Okay, so instead what we say is this particular integral. Now remember, this was just one of the integrals. This integral diverges. Why? Because it does not converge to a value. You'll find something similar on this side to occur. I'll plug in the 4 first this time, and so then I will get the negative ln of 4 minus 2, which of course is 2, right? And ironically, right? Ironically, I'm getting the values there that are going to wipe out. Moot point though. So then I plug in the g, which I'm going to get the minus and negative, so plus, and then I've got limit as g approaches 2 from the right of ln absolute value g minus 2. Since g is approaching 2 from the right, I don't actually need the absolute value here. However, just like the other one, this particular piece is still approaching that ln of 0 value, which is going to go to negative infinity. So again, the whole value of this integral also diverges. Do not make the mistake of saying, I've got a plus infinity, I've got a minus infinity, they should add out. Okay? Those infinities are not guaranteed to be the same thing. Okay? Even though there is symmetry, you could try to argue it that way, it doesn't even get that far in the calculation. The proper calculation is to complete one of these integrals, and we couldn't even do that. Okay? So the final answer on this integral would be diverges. The integral diverges, or the integral does not have a defined answer. It's unbounded would be another way to put it. This next problem is the other type of improper. You can see it right away. It has an infinite boundary on it. So I'm going to say that the domain is unbounded. That does not necessarily mean that the integral itself is unbounded. I need to actually perform it in the proper way, using limits and things like that. In this case, a lot of the work of this integral is going to come in actually doing the antiderivative, though. If you look at the body itself, that's where a lot more of my work is going to come in. So I'm going to come back to the improper portion of this problem at the end. For now, I'm going to copy it into an indefinite integral, and we're just going to work the antiderivative, and then we'll come back and handle the improper definite integral. Okay, so for just a moment, I'm only doing the integral, no boundary, of just 20 minus 2x squared all over x to the 4th plus 4x squared dx. Okay, so in this case, I'm seeing a polynomial denominator here, and some polynomial numerators too, of course. But this right here screams something that can be factored. And since I can factor it, I'll have a couple of options there. I could try trig substitution, but in this case, since there's no radicals, I'll probably have a much more efficient, quicker time if I were to do partial fractions. So that's what I'm going to do. For just a moment, I'm going to even step out of the integral itself, right? And I'm going to step away and try to just split up the fraction with partial fraction decomposition. So, start by noticing that this can be factored. So I've got 20 minus 2x squared over x squared times x squared plus 4, like so. Then, since I'm going to use partial fractions, I'll start setting up the fractions that I'm going to break it up into. I could have capital A over x. I could have b over x squared, right? Because that's the compound due to the exponent. And then here, this is a second degree that I can't split with an exponent. So therefore, I'm just going to have to do cx plus d over x squared plus 4, like so. Okay, to continue my partial fraction decomposition, I'm going to multiply everything by the x squared times x squared plus 4. So I'll multiply that to each spot here. That's going to give me 20 minus 2x squared is equal to a times x squared plus 4 plus b times x squared plus 4 plus x squared times cx plus d. And then from here, I'll employ a couple of little plug-in tricks to see if I can figure out a couple of the letters, and then some of the other tricks to figure out the others. First and foremost, I can see what happens when I substitute a value. And the first one that's very blatantly coming to mind here is 0, right? If x equals 0, then I just get 20 on this side. X is 0, so that piece is gone. X is 0, so that piece is gone. I have b times 0 squared plus 4, which is just going to be 4 times b. Therefore, b is equal to 5. We've already got one of our pieces there. That's good. Okay, so then next, I'm going to notice a few other things. First off, if I distribute this ax into here, notice that I would have ax cubed plus ax times 4. It looks like a times 4. I hate when that happens. Let's just do 4ax. Okay? Okay, so why is that important? Well, there's only one other thing that can come up with x cubed here. Let's continue distributing. I'll have bx squared plus 4b, and then I'll have cx cubed plus dx squared. Okie dokie. So then next, what I can notice is that there are 0 x cubes over here. This is 0x cubed minus 2x squared. I'm going to just divide this, not divide it, but separate it here, because this is a separate case. I have 0x cubes over here. I have negative 2x squareds. I have 0 x's, and I have a plus 20. Okay? So I can use some of this to my advantage. First thing I notice is that A and C are both of my cubes. So A plus C has to equal 0 because they're equal, and that's the only cubes that are here. A plus C must equal 0. That might help out in a minute when I'm trying to figure out the different pieces here. Next, let's look at the x's, right? Because that's there's 0 of those. That's 4ax, and that's it. Do you know? Oh, so that's key right here. Notice 4a is the only single x. Okay. Well, 0 is the only x over here. Therefore, 4a has to equal 0. Which means A is 0. But A plus Z is also C is also 0. That means C is 0 also. That's nice. Okay, so then let's finish this out. I know what B is, I know what A is, I know what C is, right? Since A and C are both 0, I can pretty much just wipe out anything with them in it. Right? C is 0, that's gone. B is 5, I know that much. And I'm looking to see what D is. Okay? Well, notice bx squared and dx squared here, and it's equal to -2. So B plus D must equal -2. But I already know B is 5. Like this. So then D would have to be -7. And of course you could have figured this out other ways, like since I already know what B, A, and C are, I could have plugged in some value for X, right? Plug in like 1 for X, if you will, right? If you plug in 1 for X, that's kind of like what you would get right here. You would get D and then the +5, because it would be the only things that would survive over here. And then of course I would subtract the 20 out, right? The 20s would go away. You'll end up with the same thing several different ways here. Okay, so let's see what this is really telling me. C is 0, right? So this piece is gone. A is 0, so this whole fraction's gone. B is 5, and D is -7. So it looks to me like I can take this integral here and rewrite it as the integral of 5 over x squared minus 7 over x squared plus 4 dx. Right? So we use partial fraction decomposition to break one complicated fraction into two much nicer, simpler fractions. Okay? So then I continue on. I'm going to do the antiderivatives here. This is really 5 times x to the -2. So what do we get? We get 5x to the -1, but divide by the new power, right? So it's negative. Okay? Minus 7 over 2. Notice I'm following a pattern here. It's going to be the arctangent of x over 2. Right? Because 4 is 2 squared. And anytime you have that sum of squares in the denominator like that with no other x's, that's your arctangent. And it's always the 1 over a arctangent and then x over a, right? And of course, since this is technically right now I'm just doing the definite integral, this is just the antiderivative. So I get a plus c to go along with that. All right, so let's finish it up then. Come back up to here, and let's do this the right way. I have to do the limit as I could pick anything really here. Let's pick. Well, I'll just pick little a again. Goes to infinity, and then it's going to be the integral from 5 to little a. 20 minus 2x squared over x to the 4th plus 4x squared dx. Of course, we've already done the antiderivative here. So then what I've got is the limit as little a goes to infinity of -5 over x minus 7 over 2 arctangent of x over 2. And then that whole thing has to be evaluated from 5 to little a. Okay. So let's list all these things out. If I plug in a, I've got the limit as a goes to infinity of -5 over a minus 7 over 2. I'm going to use inverse tangent, same thing. I'm just saving space. A over 2. So I've got to be able to do that limit minus. Now, notice both of these are negative, so I'm going to factor that out and say plus. Plus what? Plug in 5. 5 over 5 is 1. And then I've got 7 over 2 arctangent of 5 over 2. Like so. Okay, so we're almost done, right? I just need to be able to do this limit right here. The limit as a goes to infinity of 5 over a. It's a very obvious limit, right? I'm letting the denominator go to infinity. This value is going to go to 0. But then there's the arctangent. Remember, inverse tangent, arctangent is like a sideways tangent swoosh. It actually has two asymptotes, a very bottom horizontal and a very top horizontal asymptote, right? Inverse tangent does this, and it actually has a top asymptote. So this particular limit, even though a is going to infinity, I have inverse tangent of something going to infinity. That's just going to give me that upper horizontal asymptote value, which is pi over 2. Therefore, what I'm left with here is negative 7 over 2 times pi over 2. And then I've got plus all of this. And really, I mean, I guess the only thing we could have done here is maybe you could write negative 7 pi over 4. As far as the exact value goes, that's where you would stop. Okay? So then if you want the decimal value, of course you have to put your calculator into radians, because I'm going to be doing an inverse tangent here, which is going to result in an angle or a ratio of an angle, right? It should be in radians then. So here I go. I'm plunging up the negative 7 pi over 4 plus 1 plus 7 over 2 inverse tangent 5 halves. And what I'm getting is that this is approximately equal to negative 0.33177232. Okay? So of course, just depending on which way you want to represent your answer, it could be either one of those. To finish up this test, this last problem has us approximating an integral with the trapezoid rule and with Simpson's rule with 6 rectangles for both, right? 6 rectangles for one, 6 rectangles for the other. And then also I made this integral in such a way that you could also actually work the integral and get the exact value so that you could compare and see if your trapezoid and Simpson rule solutions make sense if they're really good approximations. Remember, Simpson's rule is supposed to be really, really good even for a small amount of rectangles. So let's see how close we can get to the real thing, right? Let's start with trapezoid rule. Actually, it doesn't for both rules, right? If I'm using 6 rectangles, okay, don't forget that if I'm using 6 rectangles, I've got my beginning value, which is 0, and I've got my ending value, which is 3, okay? And I'm using 6 rectangles. So 1, 2, 3, 4, 5, 6 little sections, each having a rectangle above or below them, okay? So then remember, the width on one of these is going to be delta x. So is this going to be delta x? So is this going to be delta x? Each of these widths. And we need to figure out what that is. Our delta x is 3 minus 0 divided by 6. So 1/2. Okay? That's important because delta x means the width from here to here is 1/2. The width from here to here is 1/2. From here to here is another half. So on and so on. Okay, so that means that this is 1/2. This is 2/2, right, which is 1. Then 1.5, so 3/2. And then 2. And then 5/2. And 3, right? Okay. So then I'm going to need the function values for those. Okay, let's just assign our function here. To be 1 over x plus 2 cubed. I'm going to need the function values at each and every one of these points for both the trapezoid and the Simpson's rule. Okay, so let's list those out so that we can use them. I'm going to need f of 0, right, which is going to be 1 over 0 plus 2, which is going to be 2 cubed, which is 1/8. I'm going to need f of 1/2. Okay, so 1/2 plus 2 is 2.5, which is 5 over 2 cubed, and then flipped. 1 over 5 over 2 cubed like this. So let's see, that's going to be 8 over 125. Okay, next, f of 1, right? I'm going to need, that's going to be 3 cubed, so 1 over 27. Then I'll need f of 1.5, 3/2. So 3/2 plus 2 is 7/2. So that's 1 over 7/2 cubed. So that's going to be 8 over 343. Let me double check and make sure I added that correctly. Yep, very good. Okay, so far, let's see, where am I at? Okay, I need f of 2, which is going to be 4 cubed, right? That's 1 over 64. I'm going to need f of 5/2. So then that's 5/2 plus 5/2. Oh, that's nice, isn't it? Oh, not 5/2. I'm losing my mind. 5/2 plus 2 is 9/2. 1 over 9/2 cubed. Yeah. So that's going to be 8 over 9 cubed is 729. Yum. Okay, almost there. Lastly, f of 3. I need the one on the very end. 3 plus 2, of course, being 5. I have 1 over 5 cubed is 1 over 125. Okay, so I've got the function values at each of those locations, right? I've got my function values, so that's going to be the heights of all of my rectangles there. So then I can just start setting up the rules now, right? The trapezoid rule is when I have delta x divided by 2. Okay, so be careful. Delta x is 1/2, and it's also divided by 2 in the rule. That's the trapezoid rule. Times, I do 1 time for each of the very end points. So that's just going to be the 1/8. And at the other end, I'm going to do 1 over 125 once. But then remember, everything else is times 2. Okay? So then I'm going to have plus 16 over 125 plus, because I'm doubling it, see? Plus 2 over 27 plus 16 over 343 plus 2 over 64 is 1 over 32. And then 16 over 729. And then only one of the ends. That's the trapezoid rule there. I have delta x divided by 2, and then I do one of each of the endpoints, right? So that's f of 0 and f of 3 in this case, f of a and f of b. But then 2 times this one, 2 times that one, 2 times that one, 2 times, and that's how the trapezoid rule works. Okay? Now, when you crunch this one up, I saved us some time a little bit. When you crunch this up, you get that this is equal to 0.108 729 795. Okay? So there's my trapezoid rule. Next, Simpson's rule. So I do my delta x again, 1/2, but divided by 3. And then remember what I do is one of each of the endpoints, and then I alternate between 4 and 2, 4 and 2 for each of the values inside. So again, that's going to be the 1/8, but then it's times 4. Okay, so actually I'm going to write that out this time, whereas last time I just went ahead and did it. I have 4 times the 8 over 125 plus 2 times the 1 over 27, 4 times the 8 over 343, 2 times the 1 over 64, 4 times the 8 over 729, and then I've hit the end, so it's just one of them, 1 over 125, like this. So that's our Simpson's rule setup. Okay? Now if you punch that in your calculator, this is what I got. 0.105252238. And there's your Simpson's rule answer. Now what about comparing it to the actual integral? Well, this antiderivative right here, you could do a simple substitution for x plus 2. It's to the -3 power. You just integrate it. And so what you end up with is -1 over 2, because I'm dividing by the new power. 1 over x plus 2 squared. And then I'm going to evaluate that from 0 to 3. Right? It should be equal to that. Of course, when I plug in 3, right, I get 5 squared. So -1/2 times 1 over 25. If I plug in 0, I get 2 squared, which is 4. So -4 like that. Okay? So then I've got 4 minus 25 over 4 times 25, which is 100, like so. This is going to be -21 with a double negative to come up to here, so it's just 21 over 200. And of course, if you punch 21 over 200 into your calculator, or just actually do the division, you get 0.105. Okay? So again, notice Simpson's rule got really, really close, even though we only did 6 rectangles, right? Came really close to approximating that particular integral there. So I hope these problems help you approach the studying for your test in a more organized fashion and help you in your endeavors of learning the skills for this test. And let me just reiterate, not to focus on individual questions and memorize just the questions. Focus on getting the overall idea of the skill.